Hello guys, this is the Med Dude and today we're doing Edexcel IAL Physics Unit 2, October 2021. So let's get right to it. So we have question number 1. The graph shows how potential difference V varies with current I for an electrical component. So this is the graph that we're being given. Which electrical component is represented by this graph? So what I've done is I've grabbed some graphs from the textbook, just to illustrate how easy this is if we know the graphs. So we have the IV graph for a thermistor. So because this is IV graph and this is a VI graph, so we have to take its reflection in the y in this axis, the y equals x-axis. So this will look like this. So this is a thermistor, and this is obviously not like this graph. So thermistor is off. Alright, so then we have a diode, you can see over here, and the VI graph would look a little like this. So we take same thing here, but as we know, we can tell this is not similar to this at all. So the diode is also out of the equation. We're left with an ohmic conductor. Now this is just a straight line. This is an ohmic conductor, just a straight line. So this is also this is something we also don't consider. So this is also, so we're left with filament lamp. Let's see if this is in fact correct. So we have the filament lamp over here. If we were to take its reflection in the y equals x in this plane over here, y equals x, the line, so this would look a little like this. And this is exactly like what we've been given. So the answer is filament lamp, B. Now let's move on to question number 2. So we have a student determines the wavelength of light emitted by a laser. She uses the laser, a diffraction grating, and a screen. Which of the following measurements is not required? Okay. So we can see over here, so I've shown a diagram over here. This is just to illustrate what we have in front of us. So if I was to show you what we do need, so you can see over here that there is the diffraction grating and we have the bright center spot. So let's see what they want. So they have the distance from the diffraction grating to the screen. Okay, so what are we trying to find here? They want to find what? The wavelength. They want to find the wavelength. So I just write the wavelength, and usually when we have diffraction grating on a screen, we usually using the formula n lambda equals d sine theta. Okay, so what helps us? Well, what is this d in this equation? This d over here is actually the distance between the slits. So this is distance between the slits, which in this case, as you can see over here, is d. So we can rule out d. This is the distance between the slits. So we can rule out d because we do need this to work out our lambda. Alright, what else? We also have a, the distance from the diffraction grating to the screen, which is this distance over here. Now does this help us? Yes, it does, because then it helps us to find what this angle is here. So this helps us to find the angle over here, theta here. So this distance is also important. So it is required. What about the distance from the central maximum to the first order maximum? So we have the central and the first order. Now this distance here is also this distance here. So if you look at like a triangle, this would look like a triangle from here to here to here. Now this distance is required to work out this angle. So this distance would also be required to work out this angle. And this angle will be used to tan theta to work out this angle. Right? We can use tan theta is opposite over adjacent. Opposite over adjacent. Okay, so this is also required. So we're left with C, the distance from the laser to the diffraction grating. You can see over here the distance of the laser between the laser and the diffraction grating, we don't really use this distance. We don't really use this distance over here. So what we can do, that means it's not required. So the answer by default, by the process of elimination, is C, the distance from the laser to the diffraction grating. Alright, let's move on to question number 3. So we have the equation I equals NQVA relates the current in a sample of a material to the movement of the free charge carrier in the sample. Which of the following is the correct definition of one of the terms in this equation? So we have N represents the number of charge carriers in the sample. Now the easiest way we can do is we can just rearrange the equation. So this would be, so instead of N, so the N would be N equals I over QVA. So it's the number of charge carriers in the sample per unit area. So per unit, now you can see V is also ms minus 1 times meter squared. So that will be per meter cubed. Per unit meter cubed. So not A, what about B? Q represents the total charge stored in the sample. Now that's false, because we know Q represents what? Q represents the charge. If we were to rearrange, so Q would be what? Q would be I equals NVA. Q represents what? Charge per charge carrier. Charge carrier, which is N. How many of them we have? So that's wrong. What about V? V, so we have V equals I over NQA. So V represents the drift velocity of the charge carrier in the sample. Now this is correct because V usually represents the drift velocity. I always remember drift velocity as what V stands for. So let's look at D. A represents the surface area of the sample. Now that's not correct because A represents the cross-sectional area. So the answer is C. Alright, let's move on to question number 4. So we have the temperature of a thermistor is increased. Which row in the table identifies the effect of the temperature increase on the number of conduction electrons and the amplitude of lattice vibrations? Now what is this question talking about? Now I remember that there's this acronym I remember, which is TURD. T-U-R-D. Now what does it mean? When temperature goes up, resistance goes down. So temperature has increased, right? So our resistance goes down. Now what does that mean for our conduction electrons? Now we know that R equals what? V over I. Now if this is decreasing, right, what's happening to the current? It must be increasing. Now what does current increasing mean? We know that I is what? It's the rate of charge being released per second. So if I is increasing, and time, we can't change the time, that means that the number of electrons being released are increasing. So that means that increase is the right option here. Okay, so we know that. What about the temperature? When we increase the temperature, what happens to the kinetic energy of the thermistor or the ions inside the lattice? What happens inside it? Everything has a bit more energy, right? Has a bit more energy. And as a result, what happens? Metal ions oscillate with a greater amplitude. So metal ions oscillate with a greater amplitude. Okay, so that means increases. The two ticks here are A, so the answer is A. Let's move on to question number 5. So the unit of resistance is ohm. So we got R. Which of the following is equivalent to the ohm? in these symbols. So we know that R equals V over I, but that's not enough because V over I would just be VA minus 1. But that's not enough because they want it in terms of J, C, and S. So we can break it down further. So V, what's another equation we can use for V? That is W equals QV, right? And for current, we can use the equation we used before, which was Q over T. All right, so let's rearrange. So that'll be W over Q equals V, right? So this, what are the units here? This is J divided by C. What about the current? That's C divided by S. So we're now dividing both of them. So that would mean, so V over I would mean we're dividing J over C divided by C over S. So what happens when we divide two fractions? We're times it by its reciprocal. So J over C times by S over C. So this would be equivalent to what? So we have JS, not T. So it'd be JSC to the power minus 2. Now I rearrange it because they want C in after the J. So that'll be J, C to the power minus 2, and then S. So what's that equivalent to? That is indeed A. Alright, let's move on to question number 6. So we have the speed on a vibrating string is investigated using the apparatus shown. The length of the string between the vibrator and pulley is L. The length of the string between pulley and hanging masses, which are here, L over 3. Mass of the whole string is M. Mass of the hanging masses is M. Which of the following expressions represent the speed of the waves on a string? Now, what is there a formula that we can remember which is for the speed of the waves on a string? There is such a formula, and that is V equals square root of T over mu. Now, the T is the tension, which in this case will be our weight, right? Be our weight, so that will be T equals what? What's weight? Weight is mg, right? Mg usually. Now in this case, what's the mass? This is capital M, so it'll be mg. Okay, we know that. What about our mu? So the equation here, I'll just write it here. So V equals T over mu. What's mu? Mu is mass per unit length. Now what's the length here? Is it just L? No, we also have L over 3, so we have to add them. So mass per unit length means what? So mu equals mass. What's the mass? Mass, and per means divide. Per unit length, so that will be the addition of L plus L over 3. This will give us what? 4L over 3. So this would be 4L over 3. And we're dividing by a fraction, so that's the same thing as saying M times 3 over 4L. So our mu is 3M over 4L. Right? So now we can put them all back to the original formula. So V would be equal to, so now we add the T, which is capital Mg divided by 3M over 4L. Again, we're dividing by a fraction, so B will be times by its reciprocal. So Mg times by 4L all over 3M. So that is, so we can see over here, so we need 4 mgl LGL over 3m. Alright, so that B you know, C you know, D you know, that is A. The answer is A. Move on to question number 7. So they tell us that a microwave oven has a source that emits microwaves in all directions to the oven. The diagram shows the path of 2 microwave rays that meet at point L as shown. So I'll go source, this path or source this path. The interference between the waves following these two paths could cause heating effects at L depending on the wavelength of the microwave, which row of the table is possible at point L. Okay, so they give you wavelength 24 or 18, and it's either maximum heating or no heating. Alright, so how do we go around doing this question? So first, we need to work out the path. So let's call this path, path 1. Do this in pink. So this path, this will be path 1. So what is path 1? Path 1 is 22 plus 8. That is 30 centimeters. Okay, what about path 2? You go down, you go across to L. So P2 equals what? Which is 15 plus 27. So that is 15 plus 27 is what? It is 42 centimeters. Okay. To work out anything related to wavelength, we need to work out its path difference. Delta P, do it in black. So delta P is what? Delta P is change of the P2 minus P1, which is 42 take away 30. That is 12 centimeters. Okay, so what do we do with this 12 centimeters? We can only do something with 12 centimeters if we know its the wavelength. Now in this case, let's take the first scenario, which is 24. So if we have a wavelength, right, of 24 centimeters, where would 12 centimeters lie? So that would be around about here. Around about here would be our 12 centimeters. So that's halfway, isn't it? And we know, so I usually remember it's like this. So it's 360 degrees follows 2 pi follows our lambda, our one wavelength. Now we have half of this, so that would mean 180 degrees. Pi now would be lambda over 2. Alright? So in this case, this 12 centimeters is what? It is pi phase difference. In a pi phase difference. What does it mean if something is in pi phase difference? That means what? What can we say? That means this is destructive interference. So we get what? In terms of heating, what's happening? Because if they're together, if they're superposing, if they have constructive interference, there will be max heating. If this is constructive. But we're getting destructive, so that would equate to zero heating or no heating. No heating. So that means when it's 24 centimeter wavelength, and we have 12 centimeters, this is the path difference we get over here. So we should get no heating first. So we should get 24 and we should get no heating. That is probably the right answer, but let's just check for 18. If we were to take 18, let's say we took 18. Alright, so we took 18 centimeters. 12 centimeters would be around here. Around here somewhere. 2/3 of the way. Be our 12. So this would be what? This would be 2 pi 3 phase difference. Now this is nor max. It's not max nor zero. So this is not relevant at all. Max heating and zero heating. Because this is not either pi or 2 pi phase difference. This is what we wanted, but we don't get this for 18. So 18 is already out of the equation. The correct answer is in fact C. Alright, let's move on to question number 8. So we have a current carrying wire AB of length X and uniform diameter is connected in a circuit as shown. You have AB, okay, and length X, okay. The slider S, this slider is moved along the wire until the reading on the voltmeter is 0. Which of the following equations is correct? They give you a bunch of equations. What are you trying to find here? We know that the distance between A to S, right? The distance A to S will be proportional to the distance S to B, right? There'll be a ratio. This A to S, there'll be a ratio to S to B. Because they're what? They're current carrying wires, right? They're exactly the current, and they're uniform diameter. So that means they're equally the same. So if the slider moves here, there correspondingly something would happen to R1, and it will happen the opposite to R2. So what is this distance? This distance, in case if for A to S, is Y. What about S to B? S to B is the whole thing. So over here, this is what? X minus Y. That would be X minus Y. Now what does this correspond to? So the Y corresponds to the R1, and X minus Y corresponds to R2. So our Y is R1, R2. And because they want an equation, all we have to do is just times by each other. So R2Y equals R1 X minus Y. Now they want the ratio, so it'd be R1 over R2. So that would be, so Y over X minus Y equals R1 over R2. This is the equation we want. So do we have this equation somewhere? So is it A? No. Is it B, Y over X minus Y? Yes. So that is in fact the answer. Let's move on to question number 9. So we have the wave fronts show consecutive waves approaching gaps of different sizes. Okay. The wave fronts diffract as they pass through the gap, each gap. In which diagram will the diffractive wave fronts not be semicircular? Okay. They're always semicircular unless, and only unless, what? The gap is much larger or larger than its wavelength. Okay, so let's see. So this is when, so in A, the gap is equivalent to lambda, so we will get semicircular waves. Okay, but you can see over here that the gap is greater than the lambda, so you will get something like this, not semicircular. Okay, what about C? So this is that gap is much smaller than lambda. It'll just be semicircular, right? Semicircular, circular all the way across. What about our D? Same thing, be semicircular. Okay, because semicircular, so because this is also gap equals lambda, that means B is the only one that's not semicircular. The answer is B. It's right over here, B. Alright, let's move on to question number 10. A sound wave travels through air. The diagram represents the displacement of air particles along the wave at an instant in time. There is a compression at position V. At which position is there also a compression? Now this is very easy. V, we start at V, and this is our compression, right? One wavelength later, one wavelength, or wavelength in the sense that wavelength later, this should also be a compression, because we're back at the same place that we were before. So that means the answer should be D, which is Z. And this should be our compression again. Alright, that is the end of the multiple choice question. Let's move on to question number 11. Diamonds, zirconia, and silicon carbide can be used as gemstones in jewelry. The speed of light in these materials is shown in the table. Alright. In order to identify the material used, a ray of light is directed toward the boundary between air and gemstone. So 50 air and 21 degrees gemstone. Deduce the material used for the gemstone. This is actually pretty straightforward. We have one formula that we can use, which is N1 sine theta 1 equals what? n2 sine theta 2. So now let's label what we have. So this is theta 1 equals 50, theta 2 equals 21. And we know of air, n1 is our 1. But for n2, we don't know. Okay, so now let's put it into our, let's see what we can do here. So we have n1 sine of 50 equals n2 sine of 21. Now we know n1 is 1, so that just sine 50 equals n2, and we can just put sine 21 on the other side, sine 21. So n2 is equivalent to what? So sine 50 over sine 21. When we put this in the calculator, what do you get? We get 2.13759, and it keeps going. Okay, so that's our decimal. Are we there yet? No. They've given us the speed, right? So we should use the speed to work out what we can work out the velocities and compare it to these velocities over here, the speeds here. Okay, so how do we do that? So we have, if you remember, we have this n equals c over v. This other formula that we also know for materials and boundaries between different materials. So in this case, that would be 2.13759 equals, so c is what? C is 3 times 10 to the power 8, the speed of light. 3 times 10 to the power 8 over v. Okay, what about our v? What is our velocity? The velocity is 3 times 10 to the power 8 all over 2.13759. And what do we get? We get what? 140.344840.1 meters per second. And in index notation, that would be 1.4 times 10 to the power of 8 meters per second. Okay, so we found out the velocity. Now we need to compare. 1.4 is very close to cubic zirconia. So we can say, so material is cubic zirconia. So what are the 3 marks you would get it? So the 1 mark would be to apply this formula. The next mark would be to apply n equals c over v. So c over v. And the last mark would be to get the cubic zirconia using this 1.4 times 10 to the power 8 minus 1 ms minus 1 value. Alright, let's move on to question part B. So we have diamonds are cut into different shapes, so they sparkle when the light shines on them. Diagram shows a ray of light entering diamond and incident on boundary between diamond and air. Add to diagram to show the path of the ray as it leaves this boundary. Your answer should include a calculation. Okay, what do you know about diamonds? They sparkle, right? Why do they sparkle? That's because the sparkle is really what? Light reflects internally, right? And what do we call that? What do you call that? We need to determine whether there is total internal reflection or not. Okay, so now we need to determine whether it totally internally reflects. What do we need to find? We need to find the critical angle, right? So how do you find critical angle? Do we have an equation for it? We do. We have sine c equals 1 over n, right? Do we know the n of diamond? We don't, because we only have its velocity, right? 1.24 times 10 to the power 8. So we can find out that n, right? We go n equals c over v. So it will be 3 times 10 to the power 8 all over, what did we say? 1.24 times 10 to the power 8. So this will give us what? This will give us, so 3 times 10 to the power 8 divided by 1.24 times 10 to the power 8. When you put it in the calculator, 2.419, and it goes on. So now we can go back to this formula over here, sine c equals 1 over n. So let's apply it. So it'll be sine c equals 1 over 2.419, and then there's a decimal. Alright, let's find out what c is then. C is the inverse sine of 1 over 2.41999, and this would give us 24.4 degrees. Okay, what do we do with this? We need to say something, right? This is the angle we are referring. This is the incidence angle. We need to look at it. We need to see if it's less than it or greater than it. We can say that it's since 40.5 is greater than 24.4 degrees. So what happens? So it does totally internally reflects. But are we done? No, because we need to show the path. So this path is most likely, let's just say, it's around here. And this is our normal line. And that should give you the mark. So what are the marks? Marks are saying that first calculating n equals c over v, calculating n, right? That's the first mark. 1 mark for adding the ray, 1 mark for stating that it's less than the incidence angle, and so it does totally internally reflect. So 1, 2, 3, 4. Alright, let's move on to part II. What would happen to the ray at this boundary if the material used was silicon carbide? Now what is silicon carbide? Do we know anything about silicon carbide? We know it has less velocity, 1.15. So let's look at what we would get. So this would be what? N would be what? In terms of diamonds, of C over V. This would be 3 times 10 to the power 8 all over 1.15 times 10 to the power of 8. And this would give us 2.608. And we go on. So that would give us what? That would give us, so let's just do, so the critical angle would be sine inverse 1 over 2.608. This would give us what? 22.5 degrees. And since this is also less than 22.5, what can we say? So total internal reflection would still take place. So how did we get here? We calculated its n, substituted back into this formula, find out the angle, and the angle is obviously less than the angle needed to leave. So internal reflection does take place. Alright, let's move on to question number 12. In an experiment to determine the speed of sound in air, so speed of sound in air is what usually 330 meters per second. Okay. Student held a vibrating tuning fork above a glass tube. The air column in the tube could be adjusted by raising or lowering the tube into a cylinder containing water. When the length of air column was L, stationary wave with 1 node and 1 antinode was produced. So 1 antinode, 1 node. This caused the sound to be heard. Explain how stationary waves was formed in this experiment. So in this experiment, you can see, so as it goes down, you get what? So we have a node and antinode, so that means we have 2 waves, right? So waves are reflected what? By the water, obviously. By the water. So they're traveling in opposite directions. So we have to say, and the reflected wave and the initial what? So initial wave. So what can we call the initial wave? We can just call it the initial transmitted, because we emit transmitted wave travel in the opposite direction. Travel in opposite directions, causing an interference. So we get our standing wave. So one mark is for talking about the waves being reflected by the water. Second mark is that both waves are traveling in opposite directions. Okay, move on to part B. So they tell you that a sound was heard when L was 19.3 centimeters. That is 0.193 meters. Determine a value for a speed of sound in air, and they've given us frequency. I can only think of V equals F lambda. Now, is L lambda? If you think about it, is L lambda? No, it's not, because if we take this wave, right, and then we take its, call it anti-wave, or like this, we only have from here to here, which is L. So we'll have 4 of these. So we'll have 4 L's would make 1 lambda. So that means we have to times it by 4. So 4 times 0.193 would give us lambda. So our lambda is 4 times 0.193 is 0.772 meters. So now we can work out V equals F lambda. So 440 times 0.772. This will give us 339.68 meters per second. That is equivalent to what? That we can just round it to keep it consistent. 340 meters per second. All right, move on to part II. The antinode is slightly further from the water than the end of the glass tube. Okay, so let's see. You can see over here. So if I was to show you, there is this slight gap over here and here, this slight gap. And what do they want from this gap? They're asking how this would affect the accuracy of your calculated value for the speed of sound. So if they were touching, right, this would carry on to like here or something. This would just make each node longer, right? That means that the distance between, so this would mean what? This would mean the distance, so the distance of L would increase, which means what? Which means that lambda would increase, right? Because we know that lambda equals 4L. So then what? We're talking about speed of sound, right? Speed of sound. This would result in what? Because since V equals F lambda and lambda increase, our V would also increase, resulting in what? A value which is higher, right? A higher value for the speed of sound. Now, is this more accurate or less accurate? Speed of sound. If you're further away from what it's supposed to be, and it's supposed to be what? It's supposed to be 330, and just going above it, that means it's less accurate. Which means it's less accurate. Which means the calculated value would be, so the question is how this would affect the accuracy. Means they would this would decrease the accuracy. This would decrease the accuracy. Alright, so what are the 2 marks? So we have to say the distance is increasing, and that results in lambda increasing, and that would decrease the accuracy. Okay, so that's 2 marks. Let's move on to question number 13, part A. So we have a filament lamp is marked 12 volts, 60 watts. Filament is made from a long metal with wire with a diameter of 0.25 millimeter. The metal has resistivity 5.6 times 10 to the power minus 8 ohm meter when the wire is at normal operating temperature. Calculate the length of wire in the filament. So we have to find, so this equation, this I always remember, resistivity is what? R equals rho L over A, right? But do we have everything we need for calculate the length? We don't, because we don't know what R is. Can we find out what R is using an equation? So we have V and P. Is there an equation that help us find, relates P, V, and R? There is, which is P equals V squared over R. So R would be V squared over P. So V squared will be 12 squared over 60. This is so 144 over 60. This will give us 2.4 ohms. Okay, so we got our 2.4, and that is equal to 5.6 times 10 to the power of minus 8L. What about the area? The area is what? We don't know what the area is, but we do know the diameter is 0.25 millimeter. So the radius would be half it, so 0.125 millimeters. So this just times by 10 to the power of minus 3. That's the same thing as saying 1.25 times 10 to the power of minus 4 meters. Okay, this would be pi r squared. We know the area is pi r squared. The cross-sectional area, pi r squared. This would be what? Would be 1.25 times 10 to the power of minus 4 whole squared. Now we need to work out what L is, so let's just rearrange. So L equals 2.4 pi times 1.25 times 10 to the power of minus 4 whole squared, all over 5.6 times 10 to the power of minus 8. This will equal what? So let's put in the calculator. So 2.4 pi times 1.25 times 10 to the power minus 4 whole squared divided by 5.6 times 10 to the power minus 8 gives us 2.10 meter, which is the same thing as saying 2.1 meter. So this is our answer. We get 1 mark for using an equation to work out R. Could be another equation, W equal QV, and then we work out, and then 1 mark for finding the area, and 1 mark for finding L and the final answer itself. Okay, so let's move on to part B. So we have a student has 2 filament lamps. Lamp A is marked with 12 volts, 60 watts. So here, lamp B is 12 volts and 30 watts. Okay, the student sets up circuit shown. Student states that both lamps will operate normally. Okay, what can we do with this? Evaluate whether the student's statement is correct. So we're given P, and we're given, no, this is R. We're given, no, not even R, it's V. V and P. For both, we can work out its resistance like we did before. So R is V squared over R, which we already did. So that is 12 squared over 60, which we got was 2.4, right? So that was the resistance of A. So we know that. And for B, let's look for B. That'll be what? So V squared over R. So 12 squared over 30, that'll be just double that, 4.8 ohms. So that's 2.4 ohms, and that is 4.8 ohms. Okay, so what can we say about its voltage running to it, right? So what can we say? We can say for lamp A, what about the voltage running to lamp A? What's the voltage running to lamp A? That would just be, V equals what? IR, right? Right. We know that, right? But in this case, we can say it's distributed because we know this is what? This is 1/3. This is 2/3. This will be 1/3 times 24. So there'll be 8 volts. So 8 volts are being applied to lamp A. And what about the rest? Will be 2/3 times 24 to give us 16 volts. So over here, so we get 16 volts. So what are the two values we're dealing with? We have 4.8 and 16 volts. We have 8 volts and 2.4 ohms. What's the minimum required for each? 12 volts. 12 volts. You can see lamp A has less than 12 volts. So what can we say? We can say lamp A or lamp B? Say lamp A requires less potential difference than lamp B, right? Because this is 8 volts and this is 16. It requires less, since resistance of B is greater than resistance of A. What else? What else can we say? We can say lamp A will have less than 12 volts, so will not operate normally because its requirement is 12. So operate normally. What else? So is the student statement correct? No. So student is incorrect. Student's statement is incorrect. So what can we say? We can say, so lamp A requires less PD than lamp B. Because why? Because our resistance of B is less than resistance of A. And what else? Lamp A will have less than 12 volts. So we calculated over here. Just convert to this one. So over here. So we calculated over here, which was 8 volts and 16 volts. So the student statement is incorrect. That's the third mark. Let's move on to question number 14. So we have a gold leaf electroscope is used to demonstrate the photoelectric effect. When the zinc plate of the electroscope is given a negative charge, the conducting rod and gold leaf also become negatively charged. The gold leaf deflects away from the metal stem as shown. This deviates away. The deflection of the gold leaf depends on the amount of charge on the zinc plate and the conducting rod. A beam of ultraviolet radiation is incident on the zinc plate. So here, the gold leaf immediately begins to fall back from to the conducting rod. Explain why this observation cannot be explained by the wave model of electromagnetic radiation. So what can we say about the wave, right? The wave model. That the immediately bit is the main thing, right? How can it immediately begin to fall back down if we were using the wave model, right? Because we know that the wave model, right? Wave model, how the energy distributed. The energy is spread across a wave, right? So electrons cannot be immediately released. Electrons cannot be immediately released because of this wave model. So the two marks are spread across a wave, so it cannot be released immediately. So our two marks go on to part B. So photons with ultraviolet radiation with an energy of 9.3 times 10 to the power minus 19J are directed towards the zinc plate. Calculate the maximum speed with which the electrons are released from the plate. Work function of zinc 4.3 electron volts. Okay, so what equation do we use here? We use the equation HF equals work function plus half mv squared max, right? So we know 4.3. First we need to convert this to joules. So 4.3 times 1.6 times 10 to the power of negative 19. All right. What else can we do here? We need to work out what half mv squared is. So half mv squared max equals HF minus the work function. That is just, so what is HF? That is what? What is our HF? Do we know what our HF is? Yes, we do. Given to us, this is our HF. Okay. So let's do that. And this is our work function. So this would be what? So 9.3 times 10 to the power of negative 19. Take away 4.3 times 1.6 times 10 to the power of negative 19. Okay, that's our half mv squared, right? That's equivalent to what? Half times our mass, which is mass of an electron, 9.1111 times 10 to the power minus 31. And that's just v squared max. So v max would be, so obviously it would be a square root of 9.3 times 10 to the power of negative 19. Take away. So we can just work that out. So 9.3 times. So let's work this out. That is what? That is 2.42 times 10 to the power of negative 19. Alright, so we can just do that. So 2.42 times 10 to the power of negative 19 all over what? We also have times this by 2, remember? It goes up, so times by 2. And we're dividing by 9.11 times 10 to the power of negative 31. Okay? So inside the bracket, we get, inside the root, we get what? We get 5.3128. It's a decimals times 10 to the power of 11. So let's square root it. When we square root it in the calculator, we get 728.892 meters per second. But let's convert this into index form. So that's just 7.28 times 10 to the power of 5 meters per second. Should we round it? Yes, you can see over here all one decimal place. So let's round it to 7.3 times 10 to the power of 5 meters per second. That's our final answer. That's 1 mark for this. 1 mark for HF minus the work function. 1 mark for converting this into joules. 1 mark for calculating the Vmax over here. And that is it. Let's move on to II. A student suggests that a greater maximum speed of electron could have been achieved if both a metal with a lower work function than zinc was used, ultraviolet radiation with a greater wavelength was used. Discussed in the suggestion. Let's look at the first one. So if we had a lower work function, what would that mean? That means that HF minus that lower work function would be greater than our HF minus of, which is this, of zinc, right? Of the zinc that we're doing. Of zinc, right? So this would mean what? This would mean that the Vmax also is greater than the Vmax here, right? This would result in greater velocity, right? So we know this, right? So that means this is good, right? So this is a good suggestion. What about our second suggestion? Ultraviolet radiation with a greater wavelength. What about V equals F lambda, right? If we have greater wavelength, are we going to increase speed? to increase speed, we need, let's just go back a bit. Maybe it's not the right formula to use. To increase speed, what should we do, right? What should we do? We know that to increase speed, V equals F lambda, right? And we know frequency is increasing, is frequency, because we have E equals HF, right? We need to increase this to get our thing. So V equals lambda. So we have to decrease its wavelength to get a higher HF, right? To increase our HF function. So we need what? To increase speed, we need a smaller wavelength. What else do we need? What else do we need? So the first suggestion is right. First suggestion is correct. And second is incorrect. So we can say, so what are the marks? We get 1 mark for saying this, we get a Vmax here. This is the Vmax here of the lower work function. 1 mark for saying we need a smaller wavelength to increase speed, and saying that the first is correct and the second is wrong. Alright, let's move on to question number 15. Two resistors R1 and R2 connected in parallel in a circuit. Derive a formula for the total resistance RT, total of the combination. It's actually pretty simple. So what can we say about the current in parallel? What adds up in a circuit in parallel? It's IT, right? Which is I1 plus I2, right? Now what's another formula for our current? We know that R equals V over I. So I would be V over R, right? So we know V is RT over V for R1 plus V for R2. What do you know about voltage in parallel? Since voltage in parallel is the same, you can get rid of it, right? You can just divide by it. Divide by V, we will get 1 over RT equals 1 over R1 plus 1 over R2. So that is how we prove it. Alright, let's go. The diagram shows a combination of 5 resistors. M, N, O, P, and Q. Each resistor has a resistance of 5 ohms. Okay. Show the resistance between points A and B is about 3. So this is 5 and 5. So we can combine it to get a resistance of 10 ohms. And now we need to combine it with this N. So this would be 1 over 10 plus 1 over 5 equals 1 over R. So that would be 2 over 10 plus 1 over 5 equals, sorry, no, the other way around. That would be the other way around, sorry. That would be 1 over 10 plus 2 over 10 equals 1 over R. So R would be 10 over 3. Okay, so instead of N and P, we have NPQ, we have 10 over 3 ohms. This is also 5, so we have to add this and this resistor so we can make it in parallel with this resistor. So that would be 10 over 3 plus 5. So that's what that is, 25 over 3. So N and O combine to get 25 over 3 ohms. This is 5. So now what? We do 25 over 3 ohms plus, do we do 25 over 3? No, 1 over R plus 1 over what? 1 over 5. Dividing by a fraction means going by reciprocal, so 3 over 25 plus 1 over 5 equals 1 over R. So then just times by 5, so 3 over 25 plus 5, so that'll be 5 over 25, 1 over r, so 8 over 25 equals 1 over r, so our resistance is 25 over 8, which is 3.125, so we can say resistance between A and B is what? What can we say about the resistance? We can say we can just round it to 3.1 ohms. That is our answer over here. Alright, so 1 mark for getting this, 1 mark for getting this, and 1 mark at the end to get 3.1. Alright, move on to part II. A student is told to modify the combination of resistors so the combined resistance of AB is greater than 5 ohms. She cannot change the range of resistors, but she can replace the one of the 5 ohm resistors with a 20 ohm resistor. Explain without further calculation which of the 5 resistors should she replace. So which one is the last one that we did in parallel? This was M. So if this increases, our final result will also greatly increase, right? So that means we can say over here, we can say resistor M, because resistor M, because the combined resistance in parallel by resistor M, what happens to resistor M? Will increase it more, right? More than the other ones, more than the other resistors in parallel. Resistors in parallel. 1 mark for saying resistor M, and 1 mark for saying it will increase it more than the other resistors in parallel. Alright, move on to question number 16. An atom of hydrogen has been exposed to suitable electromagnetic radiation. The atom can emit visible light. The emitted light contains a small number of different wavelengths of visible light. Explain the process that results in the emission of different wavelengths of visible light. Your answer should include a reference to energy levels. So what happens after an atom of hydrogen has been exposed? So what happens after? What happens? So this atom, or rather electrons do what? Electrons, what? They absorb photons, or we can say energy, for what? For what? They absorb energy, and in doing so, excites electrons to move up a level, to move to a, so electrons are here right now, and then they move up to this level, and then they fall back down, to move to a higher energy level. So this energy level is always fixed, so we can say which are discrete. This is the key word, discrete, or fixed values. Then they move back down. Then the electrons move back down, and in doing so, what do they do? And in doing so, release what? Release photons, right? Release photons. Now what about this part, right? What about emitting visible light? Now where did this come into all this? So now we can say, so for the hydrogen atoms, right, there are only a few energy levels, because it's what? How many electrons does hydrogen have? Right? there are only not a lot of energy level differences that can be had. There are only a few energy level differences, and because of that, that can produce visible light. Now, how do we produce this visible light? Is there an equation that links all of this together? There is one. This is because we have our E equals HF work function, and we have V equals F lambda. And since, right, let's try to work out what frequency is. Frequency is what? Lambda over V, or rather C. We want to work out what? Specific wavelengths. So let's work out wavelengths instead of working out frequency. Let's work out wavelengths. So we have our wavelength is V over F, right? So this would be what? So V over HF, right? V over HF. Lambda V over HF. Oh, is this F? No. F is E over H. So let's move it. Let's cross. This would be E, and this would be H. This goes up. So since they're only discrete energy levels, so only certain lambda are emitted, because we only have certain energy levels. Okay, so let's move on. So that's 6 marks. So we have talked about how electrons absorb energy, and because they absorb energy, they excite electron. They go from here to here in this discrete energy level. So they excite electron. So they move to a higher energy level. These are discrete. And then when they move back down, they release photons. Then we talk about hydrogen atoms. There are only a few energy levels that can produce visible light. This is because of the fact, again, that they're discrete energy levels. And because of them, we have only specific E values or energy levels that can only give us certain lambda wavelengths that are emitted. Okay, so let's move on to the next question. Part B. It's also possible to make the atoms in a sample of air emit visible light. Explain why the light emitted by the air has a large number of different wavelengths. Pretty easy. Air is a mixture of what? Gases. And each gas has a different, right? Each gas has their own different levels, right? Each gas have their own energy level, which result in a large number of different wavelengths. So large number of wavelengths. Alright, of different wavelengths. Let's move on to question number 17. A cell EMF is connected in series with a variable resistor. Resistor R as shown. The internal resistance cell is R, small r. When R is 12, so this is capital R is 12. Reading is 107 milliamps, so that's 107 times 10 to the power minus 3. That is 0.107 amps. So they give us the time, which is 300 seconds, and they give us energy, or W usually. Okay, so we need to work out what do we need to work out? We need to work out what R is, right? You know, this is IR plus IR, right? This we get from V plus IR. So how do you work out this internal PD? How do you work it out? we can use the equation W equals QV, right? W equals QV. V in this case also our E, PD. W over Q. Can we work out what Q is? Yeah, we can, because we know Q equals IT. In this case, that is what? 0.107 times 300. That gives us, we don't need to know, we can just sub it in. So what about our W? W is 50 over joules over 0.107 times 300. So 50 over 0.107 times 300. This gives us 1.5576 ... Well, since it's a big decimal. Okay, so we have our, this goes to here. We have this. What else can we do? So we can go this, we can say, what can we say? We can write 1.5576 volts, or just leave it at that, equals what? IR, so that is 0.107. What about capital R is 12 plus 0.107 times small r. So now all we have to do is rearrange to find what small r is. So that's just 1.5576 minus 0.107 times 12 all over 0.107. This gives us r. So when you put in the calculator, we got small r as 2.557 ohms, but we can round to 2.6 ohms. Right? So 1 mark for using Q equals IT, 1 mark for using W equals QV, 1 mark for using E equals IR plus big R, and 1 mark for getting this R, and 1 mark to get the right answer. Alright, let's move on to part B. Increasing capital R would make the terminal potential closer to E. Explain why with a further calculation. So we know that this is the equation, right? Capital R plus IR. And if we were to increasing R, right? R, increasing R would, what would happen? This would decrease what? Decrease this capital IR. Decrease I, really. Decrease I, which would decrease what? Decrease IR. And because it decreases IR, this means that, so PD, potential difference, is closer to our E. 1 mark for this thing, increasing R would decrease I. 1 mark that decrease R, so PD is closer to our E. So now it says a voltmeter is added to the circuit as shown. Yep, over here. Explain how this circuit can be used to determine a value for R using a graphical method. This is actually pretty simple. We're actually looking for the equation V equals minus RI plus E. So how do we get this? This is usually the end equation we would get. How do we get this? So we take readings for what? V and I as we change resistance. We change the resistance, right? And because we have taken these values, we can plot a graph of V against I. We have then this one here. All right, so we have our V, and then we have our I, and then we'll have our line. This will be our line, and then we can say gradient equals delta V over delta I. This will give us negative R. And just for your knowledge, this is our intercept E. So good. So this is how we get our 4 marks. So 1 mark for talking about the reading as we change the resistance. Second mark, draw the, so you can either plot graph or just draw it. And then last mark for getting this gradient. Let's move on to question number 18. So ICESat-2 is a satellite launched into space by NASA in 2018. One purpose of the satellite is to measure the thickness of the ice in the Earth's surface. The satellite is powered using solar panels. A laser in the satellite produces a beam of photons which travel to the Earth and back. So it travels to the Earth and then back. Calculate the intensity of solar radiation as it reaches ICESat-2. Distance of the sun. This is basically what? This is the radius, obviously. This is the power of the sun. That's pretty straightforward if we know the formula. We know the formula is what? I equals P over A. What is our P? We know the P, 3.83 times 10 to the power of 26. What about our distance? What do you do about that? Can you do anything about that? Or not? Yeah, we can. It's pi r squared, right? Pi times 1.5 times 10 to the power 11 squared. So this should give us what? So this gives 3.83 times 10 to the power of 26 all over pi times 1.5 times 10 to the power of 11 squared. Now, is this the surface? This is the what? The cross section area, right? Area is what? 4 pi r squared for a sphere. So we have to add the 4 here. So this will give us 1354.585 meter W per meter squared. And then what? Then we can round it to 1350 W meter per meter squared. So 1 mark for realizing that it's a sphere and its surface area is 4 pi r squared. So we have the value of 4. 1 mark for using I equals P over A. 1 mark for getting the final answer and then rounding it. Alright. The laser emits a wavelength of 530 nanometers. So that is, I'm just going to write here, lambda equals 532 times 10 to the power of negative 9. That is our nano. Okay. Calculate the energy. So how do you work out the energy? Energy is E equals HF. How do we work out what our frequency is? We know V equals F lambda. And in space, V is C. So C equals F lambda. So F equals lambda over C. So that will be 532 times 10 to the power of negative 19. All over what? All over what? V equals F lambda. Oh, no, this is the other way around. Mistake here. This should have been, so C equals F lambda. So C over lambda equals F. So F equals 3 times 10 to the power of 8. All over. Now what is the wavelength? So 532 times 10 to the power of negative 9. So this gives us 5.639 times 10 to the power of 14 hertz. So our energy is, so what is H? H is 6.63 times 10 to the power of minus 34 times 5.639 times 10 to the power of 14 hertz. Alright, so when you count them together, what do we get? 6.63 times 10 to the power negative 4 times 5.639 times 10 to the power 14 hertz. 3.738 times 10 to the power of negative 14 joules, which we can round to 3.7 times 10 to the power of negative 14 joules. The final answer is 3.7. And we get this from how? From using E equals HF. and then using v equals f lambda and figuring out this is the wavelength. All right, move on to part CI. The photons released by the laser are directed towards Earth. The mean time for the photons to return to satellite is 3.2. This is front and back, so this means that the time taken to reach the Earth would be half this. That would be 3.2 divided by 2, which is 1.6 milliseconds. Alright, let's calculate the height. Now this height is actually pretty simple. We just need to remember that speed equals what? Distance over time. So distance equals speed times time. That would be, what's the speed? The speed of light, so 3 times 10 to the power of 8. The time is 1.6 milliseconds, so 1.6 times 10 to the power of negative 3. So this gives us 480,000, so 480,000 meters. So we can just write out 480,000 meters. So we get this right, and we just need to use distance equals speed times time, and we know the speed is 3 times 10 to the power of 8. So when photons are arriving in satellite are detected, only those with a wavelength of exactly 532 are used in the analysis of the result. Now, what is this question all about? The question is saying that a laser in the satellite produces a beam of photon. So we only care about this laser, right? So if we go back down here, we only care about the laser. So we can write only, so we can talk about, we only want photons emitted by the laser, right? So only photons emitted by the laser should be recorded. And that is sufficient explanation. At one point, I see a sat passed over a flat ice sheet. It is 1,000 meters above sea level. Explain how the measurement taken can be used to show how the ice sheet has a flat surface and is higher than sea level. So flat surface would mean it takes the same time to come back, right? If it's a flat surface, it should take the same time to go back, front, back, and so down and back. So flat surface would mean what? Same time taken by the photons to go on same time taken by the photons to return to the satellite, And what about if we were higher than sea level? This would mean it takes less time. So if we imagine this is the sea level here, right? And then we have the ice sheet around here, satellite around here, and then around here. This takes more time. This takes less time because this is greater than sea level. We're here 1,000 meters. This should take less time. So we should say the photons should return in lesser time if the ice sheet is higher than sea level. So we can say over here, it's a flat surface with the same time taken by the photon to return to the satellite. The other one should be to return lesser time if the ice sheet is higher than sea level. So that is the end of the video. Please like, share, and subscribe, and join the Discord so you can discuss other answers and other subjects like physics, math, chemistry, and biology as well. And I'll see you in the next one.